ขอต้อนรับแขกผู้มีเกียรติทุกท่านเข้าสู่งาน JAPAN-ASEAN BRIDGES Event Series อย่างไม่เป็นทางการก่อนนะครับวันนี้เราอยู่กันที่ห้อง Conference Hall ศูนย์ประชุมนานาชาติฉลองสิริราชสมบัติครบ 60 ปีผมผู้ช่วยศาสตราจารย์ดร.ศิรวิทย์ อิทธิโสพลพิสารอาจารย์ประจำคณะวิทยาศาสตร์มหาวิทยาลัยสงขลานครินทร์รับหน้าที่เป็นพิธีกรประจำงานในวันนี้นะครับทุกท่านครับในวาระครบรอบ 55 ปีแห่งการสถาปนามหาวิทยาลัยสงขลานครินทร์ในปี 2566 นี้มหาวิทยาลัยสงขลานครินทร์ได้ร่วมมือกันกับ International Peace Foundation และได้รับการสนับสนุนจากบริษัทมิตซุยฟูโดซังจำกัดโรงแรมดุสิตธานีแอนด์รีสอร์ทธนาคารกสิกรไทยและ BMW ประเทศไทยเพื่อจัดปาฐกถาพิเศษภายใต้กิจกรรม JAPAN-ASEAN BRIDGES Event Series ซึ่งเป็นการเฉลิมฉลองการครบรอบ 50 ปีความสัมพันธ์ญี่ปุ่นอาเซียนอีกด้วยครับในกิจกรรมนี้นะครับเรามีผู้ได้รับรางวัลโนเบลสาขาต่างๆเข้าร่วมปาฐกถาพิเศษถึง 5 ท่านโดยมีคณะต่างๆร่วมกันเป็นเจ้าภาพจัดกิจกรรมดังนี้นะครับคณะเทคนิคการแพทย์ครับจัดวันที่ 15 พฤศจิกายน 2566 หรือวันนี้นั่นเองครับจะมีการบรรยายในหัวข้อ Spreading Peace Through Science and Commerce in Emerging Economies โดยดร. Sir Richard J. Roberts ผู้ได้รับรางวัลโนเบลสาขาการแพทย์ณห้อง Conference Hall ศูนย์ประชุมนานาชาติฉลองสิริราชสมบัติครบ 60 ปีคณะวิทยาศาสตร์จัดวันที่ 29 พฤศจิกายน 2566 หัวข้อ The Importance of Science for Peace Building โดย Professor Takaaki Kajita ผู้ได้รับรางวัลโนเบลสาขาฟิสิกส์ณห้องประชุม L1 ศูนย์ปาฐกถาประดิษฐ์เชยจิตคณะวิทยาศาสตร์คณะเภสัชศาสตร์จัดวันที่ 31 มกราคม 2567 ในหัวข้อ Personalized Medicine Renovation Are we going to cure all diseases and at what price โดย Professor Akron Chikhanove ผู้ได้รับรางวัลโนเบลสาขาเคมีครับณห้องประชุมทองจันทร์หงส์ระดารมคณะแพทยศาสตร์คณะเศรษฐศาสตร์จัดวันที่ 1 มีนาคม 2567 ในหัวข้อ The Prospects for Global Financial Stability โดย Professor Robert F. Engel ผู้ได้รับรางวัลโนเบลสาขาเศรษฐศาสตร์ณห้อง Conference Hall ศูนย์ประชุมนานาชาติฉลองสิริราชสมบัติครบ 60 ปีครับและคณะแพทยศาสตร์จัดวันที่ 27 มีนาคม 2567 ในหัวข้อ The Role of Basic Science in Biotechnology โดย Professor Randy W. Checkman ผู้ได้รับรางวัลโนเบลสาขาการแพทย์ณห้องประชุมทองจันทร์หงส์ระดารมคณะแพทยศาสตร์ครับโดยวันนี้จะเป็นการจัดกิจกรรมในวันแรกนะครับและท่านรัฐมนตรีว่าการกระทรวงการอุดมศึกษาวิทยาศาสตร์วิจัยและนวัตกรรมก็ได้ให้เกียรติมาเป็นประธานในการเปิดงานในวันนี้ด้วยครับสำหรับกำหนดการประจำวันนี้นะครับทั้งหมดจะดำเนินในรูปแบบภาษาอังกฤษนะครับมีดังนี้ครับเราจะเริ่มพิธีเปิดของงาน JAPAN-ASEAN BRIDGES Event Series นะครับในเวลาประมาณ 13:40 นาทีครับเริ่มจากการกล่าวรายงานโดยผู้ช่วยศาสตราจารย์ดร.นิวัฒน์แก้วประดับอธิการบดีมหาวิทยาลัยสงขลานครินทร์หลังจากนั้นจะเป็นกล่าวต้อนรับโดยท่านสุภมาศอิสระภักดีรัฐมนตรีว่าการกระทรวงการอุดมศึกษาวิทยาศาสตร์วิจัยและนวัตกรรมจากนั้นเวลาประมาณ 14 นาฬิกาครับก็จะเป็นการเข้าสู่กิจกรรมปาฐกถาพิเศษวันแรกครับเริ่มจากการกล่าวต้อนรับโดยศาสตราจารย์ดร.อมรรัตน์พงษ์ดาราคณบดีคณะแพทยศาสตร์ตามด้วยการกล่าวแนะนำองค์ปาฐกครับโดยมิสเตอร์อูเว โมราเวสผู้ก่อตั้งองค์กร International Peace Foundation จากนั้นก็จะเข้าสู่ช่วงของการปาฐกถาพิเศษครับโดยดร. Sir Richard J. Roberts ผู้ได้รับรางวัลโนเบลสาขาการแพทย์โดยการบรรยายจะใช้เวลาประมาณ 45 นาทีนะครับหลังจากนั้นก็จะเป็นการเปิดฟลอร์ถามตอบครับโดยท่านที่มีคำถามนะครับและอยากสอบถามกับทางองค์ปาฐกสามารถทำได้2ช่องทางนะครับช่องทางแรกก็คือการยกมือถามโดยตรงเลยโดยที่เราจะมีทีมงานนะครับนำไมโครโฟนไปส่งให้ท่านนะครับหรือท่านสามารถสแกน QR Code ที่ปรากฏอยู่บริเวณโบรชัวร์ที่ท่านได้รับนะครับก็จะเป็นการส่งคำถามผ่านทางช่องทางออนไลน์โดยจะมีทีมงานนะครับคอยรวบรวมคำถามแล้วก็ส่งให้กับทางพิธีกรเพื่อถามกับทางองค์ปาฐกหลังจากจบการบรรยายด้วยครับและสำหรับงานวันนี้นะครับก็จะเสร็จสิ้นเวลาประมาณ 15:45 นาทีครับโดยท่านที่ยังอยู่ในโซน VIP นะครับจะยังสามารถชมนิทรรศการ Mini Research Exhibition ได้จนถึงเวลา 16:30 นาทีครับ เอาละครับตอนนี้ก็ใกล้เวลาเริ่มงานแล้วนะครับผมขอเชิญท่านแขกผู้มีเกียรติทุกท่านนะครับที่ยังอยู่บริเวณด้านนอกนะครับให้เข้ามานั่งประจำที่ในห้อง Conference Hall เพื่อเตรียมเข้าสู่พิธีเปิดต่อไปด้วยครับและท่านใดนะครับที่มีข้อสงสัยหรือต้องการความช่วยเหลือใดๆนะครับสามารถแจ้งได้ที่เจ้าหน้าที่จัดงานนะครับที่ประจำอยู่บริเวณรอบๆได้เลยครับเอาละครับก่อนที่จะเข้าสู่ช่วงพิธีการถัดไปนะครับในการนี้ผมขออนุญาตน้อมนำทุกท่านนะครับร่วมกันรับชมวิดีโอแนะนำมหาวิทยาลัยสงขลานครินทร์เนื่องในวาระครบรอบ 55 ปีขอเชิญทุกท่านรับชมกันพร้อมๆกันได้เลยครับ
From the beginning of more than half a century, since conferring the name Songkla Nakarin, it has served as a compass, guiding the way for Prince of Songkla University, creating every mission with the benefit of mankind as a priority. In a land full of valuable and diverse cultures, from the roots of traditional knowledge combined with modern education and science systems, presenting opportunities and raising the level of equality for development in all sectors. By establishing an education system that emphasizes the multicultural exchange of diversity and a mutual understanding for harmonious coexistence in society. Prince of Songkla University focuses on teaching and learning that emphasizes the development of knowledge and skills that will be useful for future careers. Through faculty with expertise in various fields of study, focusing on the use of modern technology in teaching and learning management. Thus, students can master a variety of skills and apply their knowledge to solve practical problems, covering all fields of study. Prince of Songkla University creates a society of knowledge by providing appropriate environments for conducting research through Research and Innovation Center in variety of fields such as health science, science and technology, and humanities and social sciences, all with the goal of fostering efficient innovation and technology, ready to develop a value society, driving efforts towards becoming a world-leading research university. Prince of Songkla University plays an important role as a source of knowledge, providing academic services that cover the needs of all sectors, responding to social and economic development by coordinating with partners from the public and private sector, through innovation and technologies that are beneficial to development, while also strengthening competitiveness at regional and international levels. Prince of Songkla University places utmost importance on preserving and inheriting arts and culture by utilizing local wisdom, fostering understanding and pride in valuable local cultures, and strengthening the indigenous identity with readiness to expand and disseminate this valuable knowledge to the international community. Recognizing the outstanding potential of all areas, Prince of Songkla University reflects an atmosphere suitable for learning and self-improvement, cooperating for the benefit of mankind as one in the midst of a volatile world. Guided by leadership that aims to achieve the same goal, which is to create personal innovation to develop the southern region and the country, and convey a trustworthy academic quality at the international level. Prince of Songkla University continues its unending task of moving forward and continuing to grow alongside humanity, aiming to be a valuable university. Prince of Songkla University.
Ladies and gentlemen, distinguished guests, esteemed colleagues, and the next generation of researchers, welcome to the opening ceremony of the Japan-ASEAN Bridges event series held at the Prince of Songkla University International Convention Center. My name is Assistant Professor Dr. Sirawit Iti Soponvisan, lecturer from Faculty of Science, Prince of Songkla University, and I am proud to be your Master of Ceremony for today's event. Ladies and gentlemen, this year marks the 55th anniversary of the establishment of Prince of Songkla University. In celebration of this remarkable anniversary, Prince of Songkla University has collaborated with the International Peace Foundation, IPF, to host a series of exclusive lectures by 5 Nobel laureates at PSU Hat Yai campus. The special lectures are also part of the Japan-ASEAN Bridges event series to celebrate the 50th anniversary of Japan-ASEAN relations. Facilitated by IPF and sponsored by Mitsui Fudosan Group, Dusit Thani Hotels and Resort, Kasikorn Bank Public Company Limited, and BMW Thailand Company Limited, the Japan-ASEAN Bridges event series will take place in Japan and in Thailand, featuring events by several hosts from the two countries. At Prince of Songkla University, we are proud to announce an inspiring series of keynote talks co-hosted by our distinguished faculties, including the Faculty of Medical Technology, the Faculty of Science, the Faculty of Pharmaceutical Sciences, the Faculty of Economics, and the Faculty of Medicine. Ladies and gentlemen, the time has come for the opening ceremony of the Japan-ASEAN Bridges event series held at Prince of Songkla University International Convention Center. So first, I would like to invite the President of Prince of Songkla University, Assistant Professor Dr. Niwat Kaepradap, to deliver his introductory remarks. Let's welcome to the stage Assistant Professor Dr. Niwat Kaepradap, the President of Prince of Songkla University.
Your Excellency, Ms. Supamat Israpakdi, Minister of Higher Education, Science, Research and Innovation, Mr. Mahamat Priski Wame, Deputy Governor of Songkla Province, Honorable Dr. Sir Richard Roberts, Mr. Uwe Morawetz, Founding Chairman of the International Peace Foundation, distinguished guests, ladies and gentlemen. On behalf of Prince of Songkla University, it is my great pleasure to welcome you to the Japan-ASEAN Bridges event series. On the occasion of Prince of Songkla University's 55th anniversary, we are grateful to be able to hold 5 auspicious events under this series in collaboration with the International Peace Foundation. I am pleased to note that the underlying theme of the event aligns very well with PSU's foundational principle: work towards the benefit of mankind. Accordingly, through its 55 years of existence, Prince of Songkla University has been leading in terms of innovation, research, and higher education, both in the southern region, nationwide, and also international-wide. Hence, I am certain that the events we will be hosting now and in the coming months will both increase our institution's global visibility, research networking, and reputation, and serve as a significant milestone towards the betterment of society. Under this event, it includes a great honor and privilege for Prince of Songkla University to host the 5 talks delivered by 5 esteemed Nobel Laureates from November 2023 to March 2024. These, including the first one, today's lecture, Spreading Peace Through Science and Commerce in Emerging Economies, by the excellent Dr. Sir Richard Roberts, Nobel Laureate for Medicine, co-hosted by the Faculty of Medical Technology, Prince of Songkla University. The second is the importance of science for peace building, by the esteemed Professor Takagi Kachita, Nobel Laureate for Physics, co-hosted by the Faculty of Science. The third one, Personalized Medicine Revolution. Are we going to cure all disease, and at what price? By the Honorable Professor Aaron Chichenova, Nobel Laureate for Chemistry, co-hosted by the Faculty of Pharmaceutical Science. And the fourth one, the prospect for global financial stability, by the excellent Professor Robert F. Engel III, Nobel Laureate for Economics, co-hosted by the Faculty of Economics. And the last one, the role of basic science in biotechnology, by the Honorable Professor Randy Shekman, Nobel Laureate for Medicine, co-hosted by the Faculty of Medicine. Ladies and gentlemen, I strongly believe that the vision and insights of these world-class Nobel Laureates will inspire our faculty, students, and all participants towards achieving greater goals and elevating our community to greater heights. Before I end my thoughts, I would like to extend our special appreciation to the following person and organization. First one, Her Excellency Ms. Supamat Isarapakdi, Minister of Higher Education, Science, Research and Innovation, for honoring the event. Dr. Sir Richard Roberts, and the other 4 Honorable Nobel Laureates for sharing their inspirational wisdom with us. Last but not least, the International Peace Foundation and its team partners for starting Prince of Songkla University to make this event possible. At this moment, I am honored to invite Her Excellency Ms. Supamat Isarapakdi, Minister of Higher Education, Science, Research and Innovation, to kindly deliver the opening remarks. Please, Your Excellency. Thank you very much.
Let us all give a big round of applause for Her Excellency Ms. Supamat Isarapakdi, the Minister of Higher Education, Science, Research and Innovation.
Esteemed Esteemed President Dr. Niwat Keo Pradap, Mr. Mahamat P. Skri Wame, Deputy Governor of Songkla Province, Honorable Dr. Sir Richard Robert, Mr. Uwe Morawetz, Founding Chairman of the International Peace Foundation, distinguished guests, ladies and gentlemen, I am pleased and honored to join the Japan-ASEAN Bridges series event today. We are fortunate to have this special opportunity to listen and participate in a dialogue with Nobel laureates today and throughout the 5 events in the series. The Nobel Prize is a globally recognized symbol of intellectual achievement award to those who have, according to Alfred Nobel himself, conferred the greatest benefit on mankind. Their breakthrough discoveries and inventions have made a tremendous impact on society's progress towards peace and prosperity. That is why we are proud and grateful that Thailand and Prince of Songkla University, or PSU in particular, was chosen to host the latest in this series. It is apparent that PSU has been playing a key role in building this great nation of ours. Its innovative research, community service, healthcare, and education have all been instrumental in developing the southern region and the country. Thus, I am certain that PSU will prove to be an excellent host to meet our expectations. And the expectations are high. Throughout the 55 years of its existence, PSU has worked extensively to aid the development of the country. With these episodes of the Japan-ASEAN Bridges event series being an important contribution of PSU to Thai society that will have the entire country's attention. Yet, I am certain that we will live up to these high expectations and deliver a memorable experience for all. I would like to thank the International Peace Foundation and its partners for trusting our country to bring the brightest minds of the world together. I am also grateful to all the respected Nobel laureates for sharing their wisdom with us. Finally, I would like to congratulate Prince of Songkla University for hosting these quality events. In closing, I wish to convey my sincere wishes that these auspicious events serve as an inspiration to form productive relationships, recognize mutual goals to improve education, science, and technology, enhance the peace and prosperity of society, and ultimately all of mankind. I declare the Japan-ASEAN Bridges event series now officially open. Thank you.
Thank you, Her Excellency Ms. Suphamat Isara Phakdi and Assistant Professor Dr. Niwat Keo Pradap for those enlightening words and for setting the stage for today's intellectual pursuit. Now is a moment of gratitude and recognition. On this occasion, may I invite Dr. Sir Richard J. Roberts, the 1993 Nobel Laureate in Medicine, who is also the keynote speaker of today's event, to come to the stage to receive a token of appreciation from Her Excellency Ms. Suphamat Isara Phakdi, Minister of Higher Education, Science, Research and Innovation. This is a token of symbol of our deep appreciation for his significant contributions to medicine and his unwavering commitment to science. Thank you very much, Dr. Robert. Would you please remain on the stage? And next, may I invite Assistant Professor Dr. Niwat Kaepradap, the President of Prince of Songkla University, to come forward to present a token of appreciation to Minister of Education, Science, Research and Innovation. So this token represents our gratitude for her service in advancing higher education, research and innovation in our nation. Thank you very much, Assistant Professor Niwat Kaepradap and Her Excellency Ms. Supama Israpakdi. May I kindly ask both of you to remain on the stage? Okay. Thank you very much. And now I would like to invite Mr. Uwe Morawetz, the founding chairman of the International Peace Foundation, to join us on the stage for a photo session. And finally, I would like to invite all of our remaining honorable guests seated in the front row to join us on the stage for a group photo session. So let's capture the memories of this event together. Don't forget to look at the main camera first. So these photos capture today's spirit of teamwork and shared dedication to science and learning. It's time to celebrate our efforts. Thank you very much to all the distinguished guests who joined us on the stage. You may return to your seat as we are now preparing to get ready for the next session of the event. And that was the official opening ceremony, ladies and gentlemen, of the Japan-ASEAN Bridges event series. For your information, there will be 5 exclusive lectures co-hosted by 5 distinguished faculties at Prince of Songkla University, Hat Yai campus. Today, you are joining us for Spreading Peace Through Science and Commerce in Emerging Economies by Dr. Sir Richard J. Roberts, Nobel Laureate in Medicine, hosted by the Faculty of Medical Technology at the PSU International Convention Center. The Faculty of Science will also host the importance for science for peace building by Professor Takaki Kachita on the 29th of November 2023 at the Pradit Choidit Lecture Center, Faculty of Science. And next we'll have the Faculty of Pharmaceutical Sciences, proudly representing the talk titled Personalized Medicine Renovation, Are We Going to Cure All Diseases and at What Price? By Professor Agron Chikanover, Nobel Laureate in Chemistry on the 31st of January 2024 at Thongjan Hongladarom Room, Faculty of Medicine. On the 1st of March, the Faculty of Economics will host the Prospects for Global Financial Stability by Professor Robert F. Engel, Nobel Laureate in Economics at the PSU International Convention Center. And don't miss the role of basic science in biotechnology by Professor Randy W. Sheckman, Nobel Laureate in Medicine, hosted by the Faculty of Medicine on the 27th of March 2024 at the Thongjan Hongladarom Room, Faculty of Medicine. Ladies and gentlemen, so welcome to the first lecture of the series on the 15th of November 2023. So it is with great honor to introduce our special keynote lecturer, Dr. Sir Richard J. Roberts, the esteemed 1993 Nobel Laureate in Medicine. Let's prepare to be inspired, to learn, and to celebrate the crossroads of peace, science, and commerce. Now, I have an important announcement again, ladies and gentlemen, because following today's lecture, we will have about 45 minutes Q&A session. So should you wish to ask any question, you are invited to scan the QR code. Could you find your QR code? Find your QR code, and when you scan the QR code, it will direct you to the online submission form. By submitting your online question through that form, your question will be curated during the Q&A session, and our staff will present the question directly to me in order to ask to the speaker. Alternatively, for those who prefer a more direct approach, you feel free to raise your hand during the Q&A session, and our staff will also provide you with a microphone to voice your queries. All right, the first keynote lecture is co-hosted by the Faculty of Medical Technology. Therefore, I would like to warmly welcome Professor Dr. Amonrat Pongdara, the Dean of the Faculty of Medical Technology, to come to the stage to extend her welcoming remarks. Let's give a big round of applause for our Dean.
Esteemed President Dr. Niwat Kaew-Pradap, Honorable Dr. Sir Richard Roberts, Mr. Uwe Morawetz, Founding Chairman of the International Peace Foundation, distinguished guests, ladies and gentlemen. Welcome to the first of the Japan-ASEAN Bridges event series here at PSU, co-hosted by Faculty of Medical Technology. The occasion we have gathered to witness here today is truly exceptional. The inspirational presence of the esteemed Nobel laureates like Dr. Roberts is a true testament to the powerful role of science as a vehicle for promoting peace and prosperity. As scientists, I have personally witnessed the power of science as an unifying medium that brings together people of vastly different backgrounds for a common cause. That is the reason why all of us have been doing our utmost to create high-impact knowledge and medical innovations, alongside providing equal access to quality medical services to the people of Southern Thailand. I'm honored that our Faculty of Medical Technology is able to co-host the first of the Japan-ASEAN Bridges event series here at PSU. And I'm grateful to all who made this opportunity possible. It is my firm belief that the lessons we learn, the connections we have to make, and the bridges we build today will be the cornerstones of global peace and prosperity in the future. Thank you.
Thank you very much, Professor Dr. Amonrat Pongdara, Dean of the Faculty of Medical Technology, for setting the stage with your welcoming speech to the first special keynote lecture of the series. Now it is my honor to invite Mr. Uwe Morawetz, the founding chairman of the International Peace Foundation, to the stage to give the introductory remarks to today's event, as well as the special keynote speaker. Mr. Morawetz, the stage is yours.
สวัสดีครับสบายดีไหมครับ Welcome to the Japan-ASEAN Bridges event series facilitated by the Vienna-based International Peace Foundation. The events are hosted in cooperation with various local partners, including some of the country's main universities, and I would like to thank Prince of Songkla University for hosting our event today. Commemorating the 50th anniversary of official relations between Japan and the ASEAN region, Bridges will be continuously held in Thailand and Japan until March, involving the participation of Nobel laureates for physics, chemistry, medicine, and economics. The Japan-ASEAN Bridges series follows the series of over 800 Bridges events, which the International Peace Foundation has already facilitated since 2003 to support education in the ASEAN region. As peace cannot be achieved instantly, but is a process which needs time, Bridges has not been organized as a single conference, but as an ongoing series of events over now 2 decades, in which Nobel laureates and international decision makers have built strong bridges with leaders in all parts of society and with the general public. With the basis for peace being education and synergies being the fruit of cooperation, the International Peace Foundation has not realized Bridges alone, but has carried out the program together with UNESCO and with 179 other national and international institutions, including 106 major universities and schools across the ASEAN region. The multidisciplinary and pluralistic approach of Bridges in the Philippines, Malaysia, Cambodia, Vietnam, Singapore, Indonesia, Laos, and of the events now in Thailand reflects that peace involves all parts of society. It involves awareness and social responsibility of politicians, the business community, scientists, artists, and the media. And since peace within ourselves, our families, and our environment starts in our minds and hearts, it involves every one of us. In this sense, Bridges challenges us to cross borders and to build bridges by listening and opening up to other viewpoints, by generating new thoughts, by developing innovative forms of cooperation, and by fulfilling the desire of everyone to get to know and to learn from each other. This can lead us to a world in which we will be able to understand each other and the complexities we face today in a new light. So let us be inspired by the knowledge and the wisdom that Bridges continues to offer, an opportunity to get a more inclusive, interconnected, and comprehensive view of ourselves and the world in which we live in, and which we are able to create anew constantly through dialogues towards a culture of peace, which need the participation of everyone. I thank the 1993 Nobel Laureate for Medicine, Dr. Sir Richard Roberts, who has agreed to come to Thailand again to support the events, and we now look forward to his speech and to his important contribution to build bridges. Warm welcome, Sir Richard. ขอบคุณครับ
Ladies and gentlemen, please join me in welcoming the Nobel Prize the recipient, Dr. Sir Richard J. Roberts. Dr. Roberts is currently serving as the Chief Scientific Officer at New England Biolabs in Massachusetts, USA. He was awarded the Nobel Prize in Medicine for his pioneering work on the discovery of split genes and mRNA splicing. Educated in England, he carried out his postdoctoral research in Professor J.L. Strominger's laboratory at Harvard, focusing on the tRNAs involved in bacterial cell wall biosynthesis. From 1972 to 1992, he worked at Cold Spring Harbor Laboratory, reaching to the position of Assistant Director for Research under the leadership of Dr. J.D. Watson. He is the one who has discovered and characterized hundreds of type 2 restriction enzymes and has sequenced the complete adenovirus 2 genome. His discovery has transformed our understanding of genetics and significantly advanced the field of cancer research. Dr. Robert is here with us now to share his insight in his keynote speech titled Spreading Peace Through Science and Commerce in Emerging Economies. Dr. Robert, the floor is all yours.
Thank you. It's a great pleasure for me to be here today. I'm glad to see there are so many students in the audience, because if there's one thing that I really like, it's talking to students, because you are the future of this world. It is really in your hands whether this world is going to be successful, and in particular, whether it's going to be peaceful. And with that in mind, I definitely recommend you consider a career in science. Science is an incredibly peaceful activity. One of the things that we find as scientists is we disagree from time to time. Someone produces an explanation of something, someone else comes and says, no, that's not correct. But we can resolve these disputes peacefully. We don't find it necessary to shoot one another in order to make you believe our hypothesis. Rather, we do experiments. We produce facts, and we show what is true and what is not true. I would also say that one of the things I've noticed is that scientists make very good diplomats. Wherever we go, if we meet another scientist, we have a friend. There is nowhere in this world that I can go and not find a friend in a scientist. Scientists have been just excellent in telling politicians what is true and what is not true. And this is rather different from traditional diplomats who have to say whatever is the party line, whatever the country wants that diplomat to say. I'm not like that. No other scientist is like that. We can say what we believe. I've had personal experience of this. The Cold War with Russia. During that time, there was very little interaction between people in Russia and the rest of the world. They were simply not aware of what was going on because of censorship. But a lot of scientists went to Russia during the Cold War. A lot of people in the arts also went there, ballet dancers, artists. We were then able to talk to the Russians, to our friends, to our colleagues, and tell them what was really going on in the West. The same when China first opened up. They sent students abroad. I had 2 postdoctoral students who came to my lab at Cold Spring Harbor. We were able to make sure that they saw exactly what was going on in the West, and in return, we went and visited China. Cuba, another example. Cuba is a very interesting country, and yet even today, the US has now decided they're not going to have good relations with Cuba, and so it's difficult to get there. I've been to Cuba many times. I love Cuba. I love the culture there. I don't particularly care for the government, but they let me go. I talk to scientists there. I have friends. We help the scientists there when we can. And my company, New England Biolabs, the founder of our company, back in 1975, made it a point of going to visit Cuba to give them reagents that they needed in order to do science. And of course, in the developing world, scientists can play an incredibly important part in making sure that we have good relations, both with the countries and also in terms of our ability to spread peace, spread science, and make sure that every person in every developing country has the opportunity to grow and to develop. Now, one of the great things about science is that science leads to discoveries and it leads to companies. And I'm going to illustrate that in 3 ways, all related to my own history in science. And I'm going to start off by talking about restriction enzymes, which were some enzymes that I discovered back in the 1975, 72, to 75. A lot of these were discovered in my lab at Cold Spring Harbor. That led to some very interesting commercial possibilities, but all of you have probably heard of biotechnology. Biotechnology was made possible by the discovery of how to recombine DNA segments and how to pull out genes using restriction enzymes. These form the very basis of the biotech industry. Later on, I made a big discovery in 1977. We now know as RNA splicing. It's the discovery for which I won the Nobel Prize. And I will tell you a little bit about how that discovery took place and why it wasn't until only 6 or 8 years ago that the products of that were commercialized. So you make a discovery, sometimes you can form a company quickly, sometimes it takes you a long time before you discover the commercial benefits. But the nice thing is making the discovery, opening up possibilities. And I will conclude by talking about DNA methylation, which is something that I've been working on for a number of years now. And just in the last couple of years, we discovered something very important about DNA methylation, and also, again, a commercial possibility emerging from very basic research. I'm a basic research scientist. Even though I work for a company, pretty much all of the science that I do is very basic. Now, I'm going to talk about restriction enzymes within the context of my company, New England Biolabs. I call this section From a Basement to a Company because we started off in a basement, and now, as you will see, we've grown quite considerably. But before I start talking about biolabs, I'll talk a little bit about my own career as a postdoc at Harvard. I was trained as an organic chemist. I was lucky in that I got all of the results I needed for my PhD in 1 year. But in England, you have to do 3 years as a PhD before you can write your thesis and graduate. And so the second and third year, I started to do some experiments that I thought might be useful, were not especially useful, but they were okay. But I did a lot of reading. And this is something I would recommend to all of you. Don't just read about your subject, read about stuff outside of your subject. Because you never know when you will learn something from another discipline altogether that will be useful for your own research and for what you're doing. Or perhaps more importantly, you will find something that is even more fascinating and more fun that you can be passionate about than what you're doing at the moment. And if that happens, don't be afraid to change. And that's what happened to me. In my third year, when I was doing my PhD, I read a book by a man called John Kendrew, who was a Nobel Prize winner. He had discovered how to determine the structure of proteins. And in the process of reading this book, I became fascinated by a subject called molecular biology. The book was about the origins of molecular biology, how it all came about. By the time I finished that book, I knew this was what I wanted to do with my life. I wanted to be a molecular biologist. I talked to the faculty in the University of Sheffield at the time, and they all said there's no such subject. And there was only one assistant professor who said, well, you know, that's okay. I think it's okay. If that's what you want to do, that's what you should do. And I was passionate. This was what I wanted to do. I applied to do a postdoc at 6 different labs. At the time, you had to go outside of the UK in order to get some experience if you wanted to get a job back in the UK. I applied to 6 different labs. They all turned me down, except for one. And that one was a lab led by this man, Jack Strominger. He was at Wisconsin, at Madison, Wisconsin at the time, and he accepted me as a postdoc. And he accepted me for a very interesting reason. It was because he'd had a previous postdoc from England. And as soon as he had someone from a country who was good, he then started to take more applicants from that country. So it was just because I was from the UK that I got accepted there. Anyway, a month before I was scheduled to go, or 2 months before, he wrote to me and said, "Can you delay coming for a month because I've just been appointed a professor at Harvard," which turned out to be his lifelong ambition. He wanted to be a professor at Harvard. And when I got there, he'd achieved his lifelong ambition. He changed his field completely and he changed his personality completely also. He had a bit of a reputation beforehand of being a slave driver. You know, he would make everybody work extremely hard and tell them what to do. But he became relaxed after he got to Harvard. I was given a project to pick up from a postdoc to sequence a transfer RNA, one of these RNAs that carries amino acids into proteins during protein synthesis, except that this one didn't. This worked in bacterial cell wall biosynthesis, but it didn't work in protein synthesis, and the question was why? And so the job was to sequence this, to get the RNA sequence, and then see if from that sequence we could figure out why it didn't work. Now at the time, there was a standard method of sequencing RNA that had been developed by a man called Robert Holley, for which he actually won the Nobel Prize. But it turned out it was a slow method. It wasn't terribly good. But I read about this man, Fred Sanger. He had developed a new method for sequencing RNAs, and it sounded great. And so I decided that I would try and learn his method. He was at the MRC lab in Cambridge at the time, and I was at Harvard in the US. But I wrote to him and I said, "Could I come to your lab and learn how to sequence RNA?" And he said, "Sure." And Jack Strominger said, "Fine, I'll pay for this." And so I went and I spent 6 weeks in Fred Sanger's lab at the MRC lab in Cambridge, and I learned how to sequence RNA. Now, Sanger was a very interesting man. In many ways, he is the scientist that I look up to more than anybody else. He'd already won a Nobel Prize at the time for sequencing proteins. He developed the basic methods for sequencing proteins. He later went on to win a second Nobel Prize for developing methods for sequencing DNA, but here he'd figured out how to sequence RNA, and that was what I went to learn. Had a great time. Fred was one of the most modest people that you could imagine. When I first met him, I went into the lab and I saw a little old man who was washing the glassware. And I went and I said, "I'm Rich Roberts, I've come to work with Fred Sanger." And he said, "Oh, nice to meet you." He said, "I'm Fred Sanger." And so here he was, a Nobel Prize winner, later to win another one, busy washing the glassware in his lab. And this was how he was. He was just a very, very modest man. And, you know, if I had to pick someone I would like as a role model, it was him. He was just terrific. Now, as a result of sequencing this tRNA, and then learning how to do all of the methodology and setting it up at Harvard, it turned out I was the first person in the Boston area to be doing this. And a lot of people came to my lab to learn how to do it. One of those was an assistant professor at Harvard called Mark Potashny. And he came up to me one day and he said, Jim Watson of Double Helix fame, is looking for someone to go and work at Cold Spring Harbor to sequence SV40 DNA, and he's going to come and offer you a job. Right? But I'd never met Jim, And so I heard nothing happened. And then a couple of weeks later, Mark came and said, well, Jim doesn't actually know who you are. Perhaps you could go to his office and introduce yourself, which I did. I went to his office. Within 10 minutes, he'd offered me a job, and I was just leaving, and he said, oh, you should probably come down to Cold Spring Harbor and see what we're like, but the job's yours, he said. This isn't an interview, the job is yours. So I did. I went down to Cold Spring Harbor. I took the job there, and when I got there, he had hired me specifically to sequence this small DNA virus called SV40, which at the time was the only known virus that caused cancer. Didn't cause cancer in humans, caused cancer in mice. Now, when I arrived, I discovered there are two other groups already sequencing this virus using exactly the method that Fred Sanger had developed and that I'd learned in his lab. And if there's one thing I don't like, it's unnecessary competition. I much prefer collaboration. I'm a scientist. I want to work with people. I don't want to compete with them. And so when I got there, I remembered, while I'd at Harvard, I'd gone to a lecture by this man, Dan Nathans, in the top left-hand corner here. He had given a talk explaining how he had taken the very first restriction enzyme discovered, endonuclease R, discovered by Hamilton Smith in the bottom left-hand corner. And he had shown that this enzyme was capable of taking SV40 DNA and cutting it into a number of small pieces. And I recall talking to Fred Sanger, who said, well, the reason that he had done RNA sequencing before DNA sequencing was that there were no small DNA molecules to practice on. And all of a sudden, this gave us a way of making small DNA molecules. And so I thought, well, maybe there are more of these enzymes. There were three or four more had already been discovered, but maybe there are lots more. And perhaps we could use these to sequence DNA. And in this way, I could out-compete Fred Sanger because I could get an advantage. Well, of course, that didn't work out, but nevertheless, as a result of looking for so many new restriction enzymes, we made a series of really different discoveries. But this also was the start of an interesting relationship that I had with Jim Watson, because he had hired me to do one thing, and I was doing something else. And he got really mad about this, and he used to call me all sorts of names and threaten to fire me all the time. In fact, for the 20 years I was at Cold Spring Harbor, even when I became assistant director under him, we would fight pretty much all the time. And I think I actually learned something quite valuable from this, and that is if you really feel that what you're doing is good and you want to do it, don't worry too much about what other people are saying, okay? If you know that you're right, then stick to your guns and don't get involved with other people. Don't let them tell you you're no good. I think this is something that's actually quite important for students in Asian countries who often listen to their parents when maybe they shouldn't. Maybe they should be doing the things that they think are worth doing, not what your parents thought you should be doing. Now, this was a very interesting time between 1970, when the first restriction enzyme was discovered, and 1973, when I started looking for a bunch of them. The first useful restriction enzyme was found. President Nixon started a war on cancer and put huge amounts of money in, and it was a grant to study cancer that allowed me to get the position at Cold Spring Harbor. And then, as soon as my lab started looking for more restriction enzymes, we found that there were loads and loads of them. By 1974, this was 2 years into my tenure at Cold Spring Harbor, we'd already discovered 17 new restriction enzymes. They all recognized different sequences, and everybody was interested in them. There was an EMBO workshop held in Ghent, in Belgium. It was organized by Jeff Schell, Mark Van Montague, and Walter Fears. Jeff and Mark were the people who discovered the GMO method for improving organisms. But here we had, for the first time, this was the first public speech I ever gave about restriction enzymes. I had started organizing a little database about restriction enzymes called Rebase. I still run that today. At the time, there were about 30 entries. Now there are hundreds of thousands of entries. And I really got to know all of the key people in the field. They got to know me, and people became very interested in the enzymes that we discovered at Cold Spring Harbor. People used to come to meetings at Cold Spring Harbor, and they'd have a tube of DNA in their pocket, and they'd come down to my lab and they say, "Do you have a restriction enzyme that will cut this?" And my technician at the time, Phyllis Myers, set up a test tube rack with samples of all the restriction enzymes that we had at the time, and they would see if one of the enzymes or more would cut their DNA into useful pieces. And they all wanted these enzymes, but they were not commercially available at the time, and so we used to give them away, or we'd give them the strains and tell them how to make the enzyme, but there were many of them, and no one wanted to make them all. And so it was clear that there was a business that one could form here, that one could get a company to make all of the enzymes and then to sell them to the research community. And so I went to Jim Watson and I suggested we do this, to which he said, "No, you're crazy. This is not something you can make money at, plus getting involved with commerce is dirty. We're scientists. We don't want to get involved with the commercial world." And he turned me down. He said, "You're nuts." I don't think he wanted to fire me then, but maybe at that time, shortly after, he did. Anyway, and the model that I proposed was that this company would make money and the profits would go to support research at Cold Spring Harbor. I mean, a very simple model. We didn't have to apply to NIH for grants anymore. We could make the money that would support our research. Anyway, that didn't work out, but I was sure there was a company here. And so I talked to a friend at NIH who said, well, he'd heard that there was a company called Miles Laboratory, based in Boston, and that they were thinking of selling a restriction enzyme. And so I called them up, and they said, well, it's not actually us, it's this fellow, Don Combe at New England Biolabs. And actually, it was just called Biolabs at the time. He said, he's going to make one and sell it to us, and then we will sell it for him. And they gave me his telephone number. So I called him up, and I made exactly the same pitch to him that I'd made to Jim Watson. Start a company, we'll give you all the enzymes, we know what people want. And so I went up and met with him, and at the time, New England Biolabs was still called Biolabs. There was 3 people there. There was Don Combe, his wife, and 1 technician. They were working in a basement in Beverly. He'd used his savings in order to buy used equipment from Harvard, so he had a little lab going. He'd already made 1 or 2 products that he'd sold to Miles, but they'd not really made any money. And he was actually doing lobster fishing and pregnancy tests on the side to make enough money to keep going. And so I proposed to him that we should start the company. We should not go through Miles, don't go through a distributor. We will sell directly to consumers. And I know who they are because they've all been coming to my lab at Cold Spring Harbor with their DNA. And so that's how Biolabs got started. I produced a list of names, addresses of people who would be customers. I helped make the first catalog, shown here on the right-hand side. Don Combe, much older, is shown here on the left. This was just before he died 3 years ago. And he agreed this was a good thing to do. But the most wonderful part of it was that when he'd previously been an associate professor at Harvard, he had decided that he was going to start a company and use the profits to support research. He was a research scientist. He wanted to do research. And so here we are. We both had the same idea. Make some money, use the profits to support research. And Don had many other ideas. We became a profit-sharing company, so at the end of the year, whatever profits hadn't been spent on research or development would be shared out among the employees. We put in a very good retirement scheme for everybody. We put a daycare center in so that if we had ladies working with us who had young children, there was somewhere that they could deposit their children and then go and see them during the day if they needed to. Don was an incredible humanitarian, and he ran business exactly the wrong way. All the business people who heard about this said, this is crazy, this is ridiculous. You just don't run a business this way. You're trying to run a business to make money. You don't want to spend it on research. What's the point in that? So anyway, during the first year, this catalog and our business made $200,000. This was back in 1975. A lot of money. 1 year just starting up a business in a basement in Beverly. Now, in 1975 to 1980, we grew out of the basement. We just didn't have enough. We'd rented upstairs. There was an attic upstairs and another room upstairs. And we tried to expand, but we just didn't have enough room. At the time, we had enough money in the bank to buy this building, shown here. Oh, what's happened to it? Sorry. We had enough money to buy this building, shown here. But it turned out the interest rate on the money in the bank was higher than the interest rate we had to pay if we took out a loan from Massachusetts to build this building. Now, here's a crazy way that governments sometimes operate. They wanted to give us money so we didn't have to spend our own money to build this building. So not always the brightest thing to do. Anyway, we're in this building from 1980 to 2007. Sales shot up. The building expanded. We expanded as a company. And we then moved from 2007 into this larger building that we put up, which we're in today. We've just added a 120,000 square foot extension to this. And still, we're going to need more space going forward. When I joined the company, I was the 4th employee. I don't own the company at all. I'm just an employee. We now have 750 people worldwide working for us. We have 370 people working in this building in Ipswich, and more than 100 of them are doing research. Doing research paid for by the profits from the company. Everybody who does research has to publish their work. No one is allowed not to publish. We operate very much like a university. We have visiting scientists come in. They come and work with us. We have lectures every week. We could be a typical university department. And so these little over 100 people doing research could be on the faculty at any university that you might think of. So this has really turned out to be very good. We're very environmentally friendly. We put in a water purification plant, and now we're putting solar all over the place wherever we can. The company is really quite extraordinary. It's very different from most companies. I'll give you one example. We first started cloning the genes for restriction enzymes, so it made it easier for us to make them. One of the very first ones we did was one called BAMH1 that was quite expensive to make from its original source. As soon as we cloned the gene and learned how to make it in high volume, we lowered the price because it had been quite expensive before. And we lowered the price tenfold because we could make 10 times as much enzyme for the same effort. Our business people, our competitors, wrote to us. They said, "Are you guys crazy? Don't you understand how to run a business? You learn to make something cheaply, you pocket the profits. You don't give it back to the customers." But in fact, because of this policy that we had, we sold a lot more of this enzyme and we made more profit than we otherwise would have done just because the sales went up. And so we have never done business in the traditional way until, I would say, relatively recently, we've started doing it a little more traditionally, but that's because we hired businessmen who'd been trained in traditional business practices, and to be honest, I'm still a little suspicious of that. I think we had a pretty good model as it was. So let me tell you something about the company. So for 47 years, actually 49 years ago, we've been continuously profitable every year, except the year when 9/11 happened, when the first plane went into the World Trade Center. And basically, our ability to ship products by air stopped for about a month. It took a month before everything got back to normal. During that time, our profits were flat. It's the only time that they've been flat since we got started. The owners are the Combe family, Don Combe, his wife and children, but the employees now own about 40% of the company. And so we have a very good profit-sharing scheme. The company shares go into a profit plan for the employees. When they retire, then they can cash that in. The CEO, the current CEO, is Sal Rossello, shown here on the right. He just took over a little over a year ago, and I have a feeling he's going to be the most successful CEO we've had. Jim Ellard was quite good. Don, of course, founded it and got everything going. But Sal is really a very nice guy and is doing tremendously well. 3/4 of the staff are scientifically trained, so almost everybody who comes to work for us has a scientific background. And we have a very cooperative environment. People love working at the company. Part of this is because of the profit sharing, the daycare center, that sort of thing. But a lot of it is because of the family atmosphere that we have within the company. If ever you need someone to help you with something, you just send out an email, and usually 20 people respond and say, "Oh, I'll help." Everybody wants to help. We have a very good cooperative environment. And what you may not know is that for the COVID vaccine, 3 of the enzymes that were necessary to make the vaccine from Moderna came from New England Biolabs. One of the enzymes that Pfizer needed to make their vaccine came from New England Biolabs. And in order to satisfy the demand, because these vaccines was being spread worldwide, we had to scale up our production of these enzymes, in one case, 10,000-fold. 10,000-fold over what we were normally making to sell to the research community. And we did that because people in the company cooperated. They worked day and night, if necessary, in order to make sure that all of this happened. And we're very proud of the fact that we were able to help in this effort. The COVID vaccine was really something that was a great achievement, and I think is very good for peace also. Now we have an award-winning catalog. The catalog, we were the first company ever to put scientific information into the catalog, and everybody follows us now, but at the time, we were the first. I won't go into that too much. So after restriction enzymes, we started expanding the range of products, and so they're all listed here, loads and loads of things. And we continue to make and expand our area. We have an interesting program called Enzymes for Innovation, where we see enzymes that do interesting things on DNA or RNA or protein. We think someone may find a use for them, but we don't exactly know how it might be used, and so we start selling them to see if something can come on. One of those recently got so popular that we had to massively scale up production, and it's now in the regular catalog. We call it Enzymes for Innovation, enzymes to give you the opportunity to do things that you otherwise were not able to do. Now, NEB is a research institute. As I mentioned, we have more than 100 people doing research, just research. We have about another 80 to 100 people who are doing product development, so they're scientists improving the products that we already sell, but they're really focused on the commercial end of things. The research department is not. We're really not into doing research just in order to make money. We're doing research because there's some interesting stuff to find. So we have people working on enzymes, on gene expression, and so on. But the better feel for that can be shown here. Is this the right slide? Yes. So we've always been interested in the basic properties of restriction enzymes. We're looking for new ones, finding better ways to find new ones that would be interesting, ways that we might engineer them to make them more useful. DNA methyltransferases, which is my particular area that I love. These are the enzymes that stop a bacterium from being killed by its own restriction enzyme. I'll tell you more about that later. Genomics, we do a lot of genomics work. Filariasis. I suspect many of you have heard of filariasis. You probably heard of these worm diseases that are certainly very prevalent in Africa, but also around the world. Back in 1985, we decided we were going to have some research going on that was aimed at helping the developing world. I ran a symposium in which we got people from the World Health Organization and elsewhere to talk about the 6 major diseases that were affecting the world population. And we discovered at the end of it that filariasis or onchocerciasis was related. There was not a lot of money going into research in these areas, and we decided we were going to spend some money on it. And in the subsequent years, we have spent more money on filariasis research than the National Institutes of Health, for instance. They just didn't care about it so much because it didn't affect Americans. We have taken many routes to doing that, but one of them is to bring scientists in from the developing world in Africa, teach them, train them, send them back to Africa to do the work back in Africa. One interesting thing that came out of that is something called a LAMP assay. LAMP is an alternative to PCR. It's a way of amplifying a signal. And we used it first to develop a good diagnostic for filariasis. Worked really well. It has the advantage that you can do it out in the field. You can go out to a hut in Africa, do a LAMP test, and you will get a result. We adapted it ourselves to test for COVID among our employees. So when COVID first broke out, we were quite concerned that we didn't want to have a mass infection in the biolabs because we were busy making things for the vaccines and so on. And so 3 times a week, we tested every employee to see if they were testing positive for COVID. If they were, they got sent home. And we used this LAMP test. You can get an answer very easily. It typically takes 30 minutes, 45 minutes to get an answer. And it is really very good. And I think it helped us a great deal. It was unfortunate we tried to get the CDC to approve this in the US because it was so much better than PCR. PCR takes forever to get an answer. It's also too sensitive. It picks up RNA that's residual from COVID that is no longer infectious. But CDC weren't interested. I think there were lobbying campaigns from some of the PCR manufacturers. Anyway, we also do work on glycoproteins, DNA polymerases, RNA biology, and metagenomics. So these are new areas, some of these for us, but we've already made an impact. We typically publish maybe 70, 80 papers a year. We have a very strong publication record, and as I said before, everybody has to publish. We've also been doing a lot of humanitarian work of one sort and another. So in addition to filariasis, we've also located scientists in other parts of the world who we helped to get set up back at home. So we would have a scientist come from, say, Cameroon, come and work at biolabs, learn how to make restriction enzymes, learn what was going on, what we were doing. We'd send them back to Cameroon and give them a grant so they could get started with a company, a small company, in much the way that we started a company. And that's been quite successful too. So these are some of the countries in which we got involved in that. So now I want to talk a little bit about my discovery and the reason I got the Nobel Prize, and if you like, it's the reason I'm here, right? So RNA splicing turned out to be an incredible discovery to make. We weren't looking for it, and I think one of the things you have to realize is that almost all of the Nobel Prize winners who come and talk to you or to anybody, they won the Nobel Prize not because they were doing research that they thought was going to allow them to make a discovery and win the Nobel Prize. They did it because they were doing something totally different. It didn't work, and then they went on and made a big discovery when they were looking to see why it didn't work. And that was certainly the true in my case. So this man, Richard Gelinas, came and worked for me as a postdoc. I think he joined my lab in 1974, and started working with adenovirus messenger RNA. Now, the project was really a very straightforward one. We knew what the sequence of DNA was in prokaryotes, in bacteriophage lambda, and in the lac operon in E. coli. We knew what the sequence was that told the RNA polymerase bind here and start making RNA. It's called a promoter sequence. And the question was, in adenovirus, which is a eukaryotic virus, and in eukaryotes in general, is the sequence the same? Does it use the same promoter in both cases? And the expectation was probably yes, because all of the molecular biologists at the time would have told you that whatever is true for bacteria is true for elephants. Jacques Monod had a very famous statement about this. Everybody thought that by studying bacteria and bacteriophages, you could learn everything you needed to learn about basic molecular biology. Now, it turns out in adenovirus, adeno is a linear virus, and the transcripts come in from the end, early during infection. I had another postdoc who was busy sequencing the ends of adenovirus, and so we figured that if there was a promoter in there leading to the formation of messenger RNAs, that eventually the sequence at the end of the messenger RNA that we could determine would match the sequence on the DNA, and immediately upstream would be this promoter. And I came up with a really good experiment, even though I say so myself, probably one of the best experiments I ever thought of. And I gave it to Richard. I said, can you do this? It was a way of capturing the 5' ends of messenger RNA. And so he did the experiment and didn't get the expected result. Well, at first, when we were using the early RNAs, there wasn't enough RNA, and so we later had to go and look at the late RNAs, because late in infection, adenovirus only makes its own RNA. It shuts up all the host machinery. And so we knew that late in infection, there was something like 10, 12, 15 different messenger RNAs that were being made. And so we expected at the 5' end, at the starting point of these messages, they would all be different sequences. This is what you normally find in bacteria. This is what you find. And so we were expecting, when we pulled out all of these 5' ends, that we would see 10, 15 different spots in the two-dimensional display where we were looking at them. But we didn't see that. We saw just one. And so, I talked to Richard, and I said, well, you must have screwed up. Perhaps you can go back and do this experiment again. And so he went and he did it again and got the same result. And then again and got the same result. And I said, well, why don't you let me do it? I'll show you how to do it properly. Because, we knew we were going to get these 10, 12, 15 different spots. And so I did the experiment, and we saw just one spot, exactly as Richard had found. And so at that point, of course, I believed it, because I'd done it. And what it was telling us was that there was something wrong in our hypothesis. The idea that these RNAs all started at different points and had different sequences at the end was simply wrong. You know, the experiment, the hypothesis was a failure. And so we had to ask what was going on. So we spent a lot of time, more than a year, trying to figure out what was going wrong. And we did a whole lot of experiments that we thought of were just controls to show we were not we weren't looking at an artifact, or we were not looking at something silly. And everything said that this result we were getting said really every single late messenger RNA has exactly the same 5' end. We produced this paper, a predominant undeconucleotide, that is an 11-long nucleotide, was at the end of every single different messenger RNA made late during adenovirus infection. And there was no doubt that it was a real result, but how was it possible? What was going on? And so one of the things we came up with was the idea, well, maybe the end of the RNA is being coded in one place in adenovirus, but it's making a small RNA that then primes transcription. It sort of starts the transcript, binds the DNA, and then transcript goes on, so they all have this same 5' end. So we decided to do an experiment to test that, and the experiment to test that was to say, well, let's form a DNA-RNA hybrid between the message and the DNA, and if the hypothesis is correct, shown up at the top right-hand side over here, then there's going to be this 5' end sticking out. And if we could find the piece of DNA that was coding for that, we should be able to form a hybrid and see it in the electron microscope. So the experiment is basically shown down here. Now, neither Richard nor I were electron microscopists. And so the question really was, how are we going to get this experiment done? But fortunately, just downstairs from us, there were two good electron microscopists, Louise Chow and Tom Broker. And Louise was actually fantastic, just a really good electron microscopist. So we went down and we talked to them and we said, you know, we have this idea for an experiment. If we make the reagents, could you do it for us? And you know, they looked and they said, well, it's never been done before, but we'll try it. We'll give it a whirl. And so we made the reagents on a Sunday and Monday. Tuesday, they did the experiment, and the very first thing they looked at looked just like this. The first picture they saw, except it wasn't quite like that. Instead of hybridizing just at one point, it was hybridizing at two separate points. And so this said that this messenger RNA they were looking at was actually split into 3 pieces. And this was the discovery of RNA splicing, because we had to then explain how all of this happened. But we'd already done so much biochemistry that everybody believed the result. And you know, one of the problems with electron microscopy experiments, often you see something strange, but there's no backup. And it's just one molecule out of the billions of molecules that were in the sample. And so you have to do a lot. But we'd already done all the work. On that Tuesday afternoon, people were already talking about Nobel Prizes, because this was a big deal. And we were convinced that this was going to be a general phenomenon in all eukaryotes, because there was other data in the literature that matched up with the data that we'd found that nobody could explain. And so that led us to write this paper. It's called An Amazing Sequence Arrangement at the 5' ends of Adenovirus Messenger RNA. The term amazing has an interesting history. So when we were trying to find a title for the paper, you know, Tom and Louise and others, they kept saying, well, you know, unexpected, unusual. And I said, but it was amazing, you know, let's use the word amazing because this describes it. And so eventually they succumbed. I can be a little forceful from time to time. So we sent in the paper. 3 reviewers all wrote back and said, great work, beautiful experiments, but you know, you can't use the word amazing in the title of a paper, it's not scientific. And so I called the editor, Ben Lewin, and I talked to him about some of the other points that the reviewers had raised. And I said, you know, when you first heard about this, what did you think? And he said, oh, it was amazing. I said, I rest my case. And so that's how the word amazing got in. And as far as I know, it's the first time it's ever been used in a scientific paper. So anyway, that led in 1993 to the Nobel Prize for Medicine. I shared the prize with Phil Sharp. I'd actually known him at Cold Spring Harbor. He was a postdoc when I first arrived there as a staff member, and he later went on to MIT and independently also made the discovery of splicing. So that was all well. I have to say, the Swedes put on the most incredible party. So, you know, if you're ever lucky enough to win a prize or just to get invited to go to the ceremonies, take it. It's wonderful. There's about 10 days of constant celebrations and really an amazing experience. And then, of course, you get invited to come to Thailand afterwards to present a lecture. So that's nice too. So I want to finish up by talking about the work I'm doing at the moment, which is based on DNA methylases, DNA methylation. Now, the DNA methylases are the companions of restriction enzymes. So they operate inside a bacterial cell, and they have a small sequence that they recognize that is also recognized by the restriction enzyme, and they modify it by putting a methyl group onto one of the bases in the recognition sequence, and in this way they stop the restriction enzyme from cutting that sequence. Here's the restriction enzyme, that when a phage comes in, a bacteriophage, its DNA is not modified, and so the restriction enzyme can cut it. And so the whole system becomes a restriction modification system. The host DNA is protected, and it's the unprotected DNA from the bacteriophage that gets cut. Now, these restriction systems come in forms types 1, 2, and 3, and it's really type 2 that I want to talk to you about. Type 2 has two enzymes. One is the restriction enzyme, one is the methylase, and they independently operate recognizing the same sequence. So there's no interaction between them usually, they just recognize the same sequence. Just before I had to go to Stockholm, we made a huge discovery in this field, and that is something called base flipping. And that was made with a collaborator called Jiadong Cheng at Cold Spring Harbor. He's a structural biologist. And we've been trying for a couple of years to get a structure for a DNA methylase. And what he discovered was that when the enzyme binds to DNA, the base that it's going to modify, it flips it right out of the helix into a little pocket in the enzyme where the chemistry takes place. So base flipping, turns out, as soon as it was discovered, people were saying, oh, maybe it operates here, maybe it operates here. And we now know that almost all enzymes that modify the bases in DNA, this is the mechanism they use in order to get access to the base, because normally the bases are buried right inside the DNA. Now, methylases come in a couple of varieties. Not all of them have a companion restriction enzyme. So there are quite a few that we know of that are involved in things other than restriction. One of the best known is the DAM methylase that recognizes GATC. This is in E. coli, but it's in Salmonella. It's in most of the Enterobacteriaceae, and it's involved in mismatch repair. It marks the strands that need to be copied when repair takes place. So, you know, if you get a base mutation or something during replication, you get an error, this tells you which strand to copy. The enzyme CCRM.CCR1 is another enzyme, but this time it's involved in cell cycle control. So it controls the cell cycle within Colobacter. EcoG2 is an enzyme we discovered, modifies all A residues. We have no idea what its biological function is, but we found quite a number of examples of this. But the one I really want to concentrate on is this one down here, M.CDI1. So this enzyme is a methylase in Clostridium difficile. Now, you may have heard of Clostridium difficile. Sometimes they call it C. diff. This is an infection that if you go to a hospital, there's usually a high likelihood that you will get it. It's everywhere. It's mainly resistant to a lot of antibiotics. It's quite difficult to get rid of. And one of the reasons it's difficult to get rid of is because as soon as an antibiotic comes along, it stops growing and forms spores. It just sits there, waits for the antibiotic to go away, then it starts growing again. And the problem with it is it causes uncontrollable diarrhea. And so people who get it, they go home, they continue to take whatever medications they take, but they never leave the house again because they never know when they're going to suffer from diarrhea. And you don't want to be in a public place when this happens. And so they just stay at home. Devastating, really awful disease. Turns out that this enzyme controls sporulation in C. difficile. So when this methylase is present, the signal from the methylase tells C. diff, this is how you turn genes on and start sporulating. If you knock out that methylase, C. diff cannot sporulate. And so you can imagine if you had a good inhibitor for this enzyme, it would stop C. difficile infection. So you could add antibiotics, you could add this new compound, and away you'd go. We discovered this enzyme in my lab 2 years ago. We have been collaborating with people, we published it, and it turns out that there are now 2 clinical trials underway from groups that have found an inhibitor for this enzyme. We don't have the results yet. We don't know if it's going to be specific enough, if it will be FDA approved. But it just tells you, as a scientist, this is what I love to do. I go into the lab, well, actually, I sit on my computer every day, and I'm looking for things like this. There are hundreds of methylases like this that are not part of the restriction systems, and most of them, we have no idea what they do. And I'm hoping that I will find out what some of them are doing. I'm hoping that some of you will find out what these things are doing, because there's a wealth of potentially good medical interventions that could come from identifying what's going on here. So I will stop at this point. I thank you very much for your attention, and I'm more than happy to take any questions that you might have. So thank you very much.
What a brilliant speech by Dr. Sir Richard J. Roberts. Can we have a big round of applause for him again? Now it's time to open the floor for a Q&A session, which we have about 30 minutes for questions and answers. We do have lots of questions submitted online, but first, let me hear from the live audience sitting at the conference hall first. I'll give you one question. So if anyone here would like to ask that question in person, just raise your hand without the need to scan the QR code. Anyone would like to ask a question in person? We'd love to hear from you. Okay, there we go. This is your good opportunity to engage directly with the speaker.
Thank you, Dr. Roberts. I think your talk can also be described with the same adjective. It was amazing. I'm Josh from the PSU International Affairs Office, and what I found particularly inspirational about your talk is how you turned that one failure in the past into an opportunity and eventually into success. And I think it would be quite useful for all of us to know more about how this happened. And because at that point, normally, most of us would just say, okay, this doesn't work, let's move to something else. And what was that motivation that made you stay on that path? And theoretically speaking, if you didn't have that breakthrough, would there have been any point that you would have said, okay, let's try something else? Thank you.
Okay, well, I'm a great believer in failure. I think failure, if you do a post-mortem every time you fail and find out why you failed so that you really understand what was the cause of it, you learn. This is how you learn. If you look at the vast majority of businessmen, when they start their first business, it's a failure. But they learn from it. And the next business is either successful or it doesn't fail for the same reasons. Business constantly fails, and failure is great. I love it. I love it when students come to me and say, you know, well, you'd suggested this experiment and I did it and it didn't work. And I always think, well, nature's trying to tell us something here. You know, I'm optimistic. I love it when students come and say I failed, because I tell them, go back, make sure you did the experiment properly, make sure that you didn't, you know, do something silly. And if you can repeat the failure, then figure out why. Why did it fail? And so I think this relates to the whole issue of you have to be very careful when you're doing experiments to make sure you follow protocols, you write down exactly what you did so that you can do a post-mortem. It's kind of interesting. In the aircraft industry, every time a plane crashes, there is the most incredible post-mortem done. They check absolutely everything to find out why it went down, and then they fix it and make sure that that fix is applied to other planes. This is why flying in planes is very safe. Unfortunately, in medicine, you can't always say the same thing, because a lot of doctors both feel and are taught that they should never admit that they failed, because then you lose the faith that you have with the patient. And I think this is a big mistake. But it's partly because of human nature. You know, a lot of parents, they tell their kids, you fail, you're no good, and they chastise them. Failure is great. I love failure. And I gave a talk in Dubai not too long ago to a lot of young people. They were called young geniuses, but it turns out they were just young kids who had greatly exceeded all sorts of expectations. And afterwards, I got an email from the mother of one of these kids who said that the child wanted to talk to me. And so we set up a Zoom call, and he told me that what he loved to do was rollerblade rather. And there was a particular trick that he wanted to do, and he'd been afraid to do it because he didn't want to fail when he was doing it. And after hearing me talk, he said he went home and he tried it, and it succeeded. And he said if he'd not heard me talk, he wouldn't have tried. So I felt this was great. So don't be afraid of failure. You should embrace failure. Failure is really good. So does that answer your question?
Perfectly well, thank you.
Okay, thank you.
Thank you, Dr. Robert. So all the students here, as well as the researchers, remember his words, don't be afraid to fail. Now let's go back to the online question. We have one question here, and it reads, in my experience, the mindset that scientists should not be involved in business is going strong here. How did you deal with such opposition back then, and what can we do to break down that mold?
Well, I'll tell you a personal story, and then I'll tell you what I learned from it. So when I first got involved with New England Biolabs, almost all of the senior people at Cold Spring Harbor told me that I was crazy, that I shouldn't be doing it, this was not how to do so, exactly what the question said. And in fact, at the time, the assistant director, Joe Sambrook, talked to the board of trustees of Cold Spring Harbor Lab and tried to get them to fire me because I was getting involved with business. And I went up and I sat in front of the board of trustees and I talked to them about what was going on. And then afterwards, the chairman came over to me and he said, don't listen to these people. Business is good. What you want to do is really good. Just don't listen to them, he said. That's my advice. Don't listen to these people who tell you not to get involved in business. Business can be good. It doesn't have to interfere with your research. You know, in my case, I just became the chief advisor to New England Biolabs at first, and then I went on to make my Nobel Prize-winning discovery. I chose that route because I wanted to do science. I love doing science. You know, I like it so much, I don't think I've worked a day in my life. I love science. I like to get up in the morning, get on my computer, make a discovery, and I make one almost every day. I love it. You can too. Okay?
Okay, so do what you love, basically.
Yes.
Okay, coming up next to the questions number 2 is, what is your perspective on future collaborations between chemistry and medicine?
Well, there's really an awful lot of opportunity in medicine for chemicals to help. I think I gave you an example here with C. difficile, right? The compound that they found that inhibits the methylase is a small molecule. Small molecules can be really helpful, and they're good in the sense that they're easy to make, usually, and so you can make them in bulk and make plenty of them. But there are plenty of things that go on in biology and in medicine that are more complicated. So you need antibodies, proteins, larger molecules in order to do it, and here you kind of have a biological solution. But I think there are many, many cases where you can find chemicals that will interfere with key processes that are perhaps causing disease. And one of the really exciting developments recently is something called AlphaFold. You've probably all heard of AlphaFold. This is a way of predicting how proteins fold, and it really is very powerful. But what it doesn't yet do is to tell you in depth how a small molecule comes along and interacts with a protein, and what happens when the two interact. And I think this is going to be the next development. There are a lot of people working on this at the moment. There is no really good solution for this. But once you can do that, once you can do a computer simulation and know what sort of molecule will interact with a protein and cause changes, then you have lots of opportunities, I think, to figure out how chemistry can be really helpful for medicine. So just watch this space. Watch the scientific literature.
Yeah, so there's opportunity to collaborate between the chemistry and medicine. We do have lots of participants from the Faculty of Science and also from the Faculty of Medical Technology and the Faculty of Medicine, so maybe it's a good time to think about future collaboration as well. Okay, moving on to question number 3, we have, what non-science skill set did you find most useful in your commercial ventures? Let me repeat the question again. What non-science skill set did you find most useful in your commercial ventures?
Well, I think for me, that there were a couple of things. One is knowing what scientists need. So, people were all coming to my lab. They wanted access to the restriction enzymes. But I know they want access to other things too. And so going around talking to scientists, finding out what can really help them in terms of doing experiments, this is really invaluable. I mean, this is very, very good. And so that can be great. I think I would also go back and reiterate, not necessarily listening to businessmen all the time, and certainly not listening to venture capitalists, can be very good. Most people who want to put money into a company think they're going to build a billion-dollar company, right? This is their mindset. Money, money, money. How can I make more money than is possible? But you don't need to make a lot of money to be happy. When we made $200,000 in the first year of operation of Biolabs, we thought we had really made it big. We thought this was big time. We never imagined we were going to get to be the size we are at the moment. And you don't need to be huge. You don't need to set your sights on massive profits and massive amounts of money. I think if you can form a company, you can do something that will help people. In our case, we were helping molecular biologists to do science. You can get tremendous satisfaction out of that. And I've always felt this is why I went into business. Because I just wanted to help other people to do science. We wanted to make sure the reagents were available at prices they could afford, and in particular, the reagents they needed, the ones that were important for science. So we've had a big philosophy always of going out and talking to our customers, finding out what they really need.
Okay, thank you. The next question is also related to the previous question. Could you please elaborate on turning a scientific discovery into a marketable product? And how did you deal with challenges such as intellectual property protection, scalability, and the complex regulatory environment?
Right, well, when we first got started, we didn't patent anything. And that was a decision that I made right from the very start when we found these enzymes, because we thought that it was most important that a number of companies took a shot at making them, and the ones that could make the best quality product that worked every time were the ones who would get the business. And we wanted to make sure we were that company. But we didn't want to put intellectual property in the way, and I think IP often gets in the way of innovation. IP is not something that I'm a big fan of, so I try to avoid it whenever I can. Our company doesn't feel the same way, but I'll tell you an interesting story. When we were probably 10 years into our business, a Japanese company and a German company patented a restriction enzyme. And everybody else had not done it because I found out about it ahead of time, talked to them and said, we weren't going to do it, you shouldn't do it. And the big companies, they didn't do it. These two small companies did, and it scared everybody. And it made everybody, whenever they found a new enzyme, to now try to get IP on it, try to get patent rights and so on. Those two companies went out of business after 3 years. So the patent did them no good whatsoever. And instead, what it did was to make the rest of us start to apply IP, and in the long run probably cost the consumers more money. It was a stupid decision, absolutely stupid. So I think you can get away without IP very often.
Okay, thank you. Maybe it's good time to switch from online to offline question again. Anyone would like to ask a question in person? Feel free to raise your hand. Anybody?
Thank you. According to your speech and valuable works in the past, what strategies have had the biggest impact on your success? Thank you.
Well, maybe I'll give you a little autobiography here. So, when I was a kid at junior school, about maybe age 8 or 9, the headmaster used to give me little puzzles to do at night. They were pretty much all mathematical puzzles, and I loved them. I fell in love with mathematics. And then my father bought me a book called How I Became a Detective, How I Became a Traditional Detective. And prior to that, I thought mathematics was going to be where I was going, but I read that, I said, I'm going to be a detective. I thought this was fabulous. It sounded really good, solving puzzles all the day and getting paid for it. You couldn't beat that. Then my father bought me a chemistry set, and I discovered you could make explosives and fireworks. And this was in the days when chemistry sets really were chemistry sets. They were great, none of this tame stuff that you can buy today. And so then I decided I was going to become a chemist, and that stuck with me until I went to university, got my PhD, and then I became a molecular biologist after reading a book again. And so I've always felt it's very good to read around your subject, to read about other things, and you never know when you're going to find something that either is useful for what you're doing at the moment or you want to just change altogether. And to be honest, I love it when people tell me I shouldn't do something, because I always think that probably means it's really worth doing. And when they tell me, oh, why don't you do this? I never want to do that because they thought of it. I want to do something that I thought of. And so I don't take advice very well. You should ask my wife about this. She will give you the lowdown on that. But I really do not like listening to what other people are following their ideas. I want to follow my ideas. And very often that means they're going to tell me I'm wasting my time. Well, if I'm wasting my time, too bad. But most of the time it's played out really well. And I don't consider I've wasted a day in my life. I'm the luckiest guy you know. I've had the most amazing career. And if you want to know about a piece of luck, on 9/11, the first aircraft that went into the World Trade Tower, I was booked on that until 2 weeks before it took off. And I was going to a meeting in California. The meeting got moved forward by 1 day, and so I took that plane 1 day earlier. That is luck.
Thank you. Now let's get back to the online question. This question is, I think it's a bit personal. So what challenges did you face when training scientists from the developing world, I think it's Thailand or somewhere in Southeast Asia, and how did you track their progress once back in their home country? Did they do well?
Okay, so I've had 3-4 students from developing countries who did their PhD. They basically did the research for their PhD with me, but then went back to their home country and sort of did the coursework and so on and everything that was necessary. 2 of those have done really well. 1 of them not so well. And the 4th one really wanted to set up a company, tried really hard to set up a company, but was not able to. But now she is working in Cameroon at the Chantal Beer Center, where she's a principal investigator. So she's doing really well, but just not in the way in which we expected. But I always keep in touch with my students. Whenever, anytime they write to me, I always write back immediately. I'm pretty good at that. So I try to keep track and help whenever I can.
Thank you. Moving on to the next question from online. How can companies effectively support education and research initiatives in a way that benefits both their business interests and the broader scientific community?
Okay, well, I think one of the things we've done, a lot of the people who came to work at biolabs in the early days had a bachelor's degree, but they didn't have a PhD, and yet they expressed some interest in doing research. And so we would always sponsor them to go to a local university and get a PhD and then come back and work at the company, and we still do that. We have people still. We also set up an educational program with 2 universities in France where they would send their students to biolabs to do the practical work, but they'd get their degrees back in France. And quite a lot of those people came over initially to do as part of a master's degree, and then came back and wanted to do research to do a PhD. So quite a lot of them have gone back and gotten PhDs. And one of the most recent people who've come is absolutely fantastic. And so we've made a huge effort to recruit her, which she currently has done. But she keeps talking about going back to France to do her work, and we're trying to figure out how to make sure she doesn't do that, but stays working with us, because she's terrific. So,
thank you very much. Now, next question is a bit more academic. It's about cryonics. So the question is, do you think cryonics is possible? Will human cells or DNA survive through the years of frozen stage and be revived in the future? Will the person who undergo this service be the same person with memories and characteristics as the one before put into the process?
okay, so I'm not sure I completely understand the question. So are you asking, is it going to be possible to engineer people using modern gene technologies? Is that what you're trying to get at?
Well, if I understand, I think cryonics is like putting people into the refrigerator or something to freeze them.
Oh, just preserving them?
Preserving them.
Yeah, I don't know why you would want to do that.
This is from the audience.
I mean, I can think of some people. There's actually, I'll tell you a very good joke. I love jokes, by the way. It's a very good joke. There's a parrot, and it's really using very bad language and screaming at its owner. And after a while, the parrot, the owner says, I'm just going to put you in the freezer and I'll teach you to do something. And so he goes in and the parrot is squawking for a while and then it shuts up and never says anything. And so the owner pulls open the freezer and the parrot looks at the owner and he says, see that turkey in there? What did he do? No, you don't get it? Okay. turkey was frozen, being kept for a special occasion. The parrot thought that that was why he'd been put in the freezer. Okay, go on. Let's
Okay.
try another one.
All right, let's go back to the offline question. Anybody would like to ask a question? Here we go. We have that gentleman. Can we have a microphone for him, please?
My name is Prasik. I'm a University Council member.
I can't hear you. Do you have to put the microphone on? Yeah.
My name is Prasik. I'm University Council member. I thank you for a very inspiring lecture. I am a molecular biologist, actually, and make failure enough to be a professor. So, my question is, there's many students here. People now seem to feel that students seem to feel that they should go to, say, AI, computer science, but I believe that molecular biologists still have a lot to do. So basically, I would like you to give some advice. So if some student would like to go to molecular biologists today, what are the futures of them in the next, say, 20, 30 years?
Okay.
That the challenge is still there.
Okay.
Thank you.
So I'm a big fan of AI. I like AI. In fact, I'm thinking of switching and doing a lot of AI myself, to be honest. And I think it can be incredibly helpful for biology in general, any aspect of biology. But the problem with AI, and certainly generative AI at the moment, is that the databases upon which the programs work are not very good. Okay? They're full of rubbish. You know, they just pull stuff from Google, they pull stuff off the internet. A lot of the underlying information is not accurate, and so you're not going to be able to make accurate, solid predictions unless you have a good factual database to start with. So one of the things we can do in biology is make sure that we have and develop some good factual databases upon which these algorithms can operate. And then the second thing we need to do is to make sure that when the programs run, especially generative AI, they tell us how they're making those decisions. We need to know how they work. And unfortunately, a lot of computer scientists aren't interested in that. They just want to get the answer as fast as possible. And the steps are all hidden. You don't know how these algorithms are making their predictions. And I think it's important that we figure out how to do that. This is something for computer science to do. They probably think it's boring, you know, it's not interesting, it's not cutting edge. But that is the way in which the only way we're ever going to be able to know whether predictions are true, whether they're really good. Let's have a good factual database, and let's know how the algorithms work and how they make their decisions, and then it will be great. But the nice thing about all of this is that as soon as you make a prediction, you have to test it experimentally. And this is something that there's not enough going on at the moment. Loads of bioinformaticians, they make predictions, they're not testing them. If they're not tested, you have no idea whether they're true or not. So we will always need experimentalists in biology, molecular biology, in anything, to test the predictions that come out of AI. But with all that said, I'm a fan of AI. I think it's got a great deal of potential.
Thank you very much. Now let's get back to the question submitted online. This one is also related to prediction. Is how could you discover the enzyme in that decade? Do you use the traditional way or some kind of computational molecular docking to design the target enzyme, then to create the protein?
So start the question again.
To start the question again, so how could you discover the enzyme in your decade?
Okay, that's what I thought you said. Okay. Well, you know, we did experiments, right?
And did you use the bioinformatics tools?
No, bioinformatics didn't exist in those days. So the very first computer programs were some that I actually was involved in writing back in 1976, 1977, 78. We wrote programs to predict restriction enzyme recognition sites and also to assemble DNA sequences. We were one of the first labs to be developing programs that could generate sequences and put them all together. So I've been in bioinformatics way too long.
All right, thank you very much. Now, another question is, are there specific areas of healthcare where the application of methylation-based therapies hold particular promise? And if so, what are they?
Well, I think infectious diseases are the obvious ones. C. difficile is an infectious disease agent. I don't know that methylation is going to be useful everywhere, but there are so many of them that they are certainly affecting how bacteria work, and they're controlling aspects of bacteria. We just need to do some experiments and find out. Bioinformatics isn't going to tell us. It can tell us when there's something interesting going on, but you need to do the experiments to find out what it is, and you need to devise some good experiments to test that.
Thank you. And there are two more questions left. So one of them is, in your opinion, between competition and cooperation, which one will be better for running business? Is the same answer for the ones who are doing research?
Well, you know, businesses like to compete, okay? But on the other hand, we found that collaboration has often worked quite well for us, and we do collaborate with quite a number of other companies over the time. Personally, I don't like competition. Why compete? Why do the same thing that somebody else is doing? You know, why not just do something that is unique to you that will benefit people? And I definitely feel in research that that is the way to go. I do not like competition. And in fact, a lot of the research that I do looking at DNA methylation in bacteria based on sequence data is done in collaboration with scientists around the world. I think the last time I counted, I had almost 200 collaborations going with scientists around the world. They send me their data, I do the analysis, I send the analysis back. Some of it gets published, some of it gets used in what they're doing, but I love collaborations.
Okay, thank you. And one more question is, do you have any guidelines for finding good topics for research that can be beneficial to humanity in the future?
The bottom line there is probably not. You never know. You know, you do your research because you have some underlying interest. I don't do research to try to help humanity. I do research to try to find out how things work. You know, I'm kind of hoping that before I die, we will figure out how a simple bacterium works. And by that, I mean we can write a computer program that will behave and respond in exactly the way that the bacterium would respond to whatever signals we put in. That's what I'm interested in. I want to know how things work. So I think it's a good model. Business and other things, medicine, that comes later. But when you see opportunities, I mean, you just have to look at your results and you can see, is there an opportunity? If there is, take it. If not, then just continue making discoveries, having a good time, having fun. I tell you, science is such fun. It's incredible.
Thank you. And this is maybe the last online questions as we are running out of time. So your last question is, based on your extensive experience in science and research, what are some key lessons that you have learned that could be applied to promoting peace and economic growth in emerging economies?
Well, I did try to give you some indications here. Science is universal, okay? Wherever you go, you have a friend. All you've got to do, go to a local university, look up the science department, you have friends. We want to make peace. And I think you'll find that scientists are very good at telling politicians the truth. And part of the problem is a lot of politics doesn't deal with the truth. A lot of politicians don't want to know the truth. They just want to tell you their side of the story and have you believe it. And so when a diplomat from another country goes and talks to a politician, they tell them the country's line. They don't tell them what is true. But if I go, I tell them what is true. I tell them what I know, what science is telling me, what they should do. If you look at the way the US responded to the COVID pandemic, it was terrible because the politicians didn't listen to the scientists. And I always ask, if they don't want to listen to us, why do they fund us? What's the point in funding science if you're not going to listen to the facts that come out from science? And so I have an interesting proposal for a law. The law would be, if a politician lies, you should be able to sue them and send them to jail. Do you think any politician would ever support that?
Okay, thank you very much. It seems that the Q&A sessions needs to be stopped now as we are running out of time. So thank you all the participants for the engaging Q&A session. And can we also have another big round of applause for Dr. Sir Richard J. Roberts, please?
Thank you. Thank you.
And now I would like to invite Assistant Professor Dr. Niwat Pradap, the President of Prince of Songkla University, to come to the stage to present a token of appreciation to Dr. Sir Richard J. Roberts,
Okay.
the 1993 Nobel Laureate in Medicine.
Thank you.
Okay. Thanks.
It's fine. It's our local product.
Okay.
This is our way of extending a heartfelt thank you to Dr. Roberts for enriching us with his extraordinary keynote lecture.
Okay. Thank you. Thanks.
Thank you very much. Would both of you please remain on the stage? And next, I would like to ask Professor Dr. Amonrat Pongdara, the Dean of the Faculty of Medical Technology, to come to the stage to present a token of appreciation to Dr. Sir Richard J. Roberts, please. This is another token to represent our gratitude and appreciation from the Faculty of Medical Technology. So through this token, we are honoring Dr. Roberts, whose work inspires us all to keep exploring and making new discoveries. And next, I would like to invite Mr. Uwe Morawetz, the founding chairman of the International Peace Foundation, to join us on the stage for a photo session. And also would like to invite Ajahn Prasit and Ajahn Rirasak to join us on the stage as well. Our warmest thanks to Dr. Roberts and Mr. Morawetz for your leadership in promoting peace through science and knowledge, and for your invaluable contribution to today's event. So ladies and gentlemen, as we come to the end of the first keynote lecture, I would like to extend our heartfelt gratitude for your participation. We hope this event will ignite new ideas, inspirations, and collaborations in the future. Now I have another important thing to announce. You may notice that there is also another QR code on the leaflet provided, and that is the one for giving us your feedback. So by scanning the QR code and filling out the online evaluation form by 5 p.m., repeat, by 5 p.m., you not only help us enhance our future events, but also secure your e-certificates of participation as a memento of your engagement today. Repeat, the feedback must be provided by 5 p.m. today in order to receive your e-certificate. To our esteemed Nobel laureates and all the distinguished guests sitting in the VIP zone, now is your time to enjoy your coffee break and the mini research exhibition located on the right side of the conference hall. Let this be a time of celebration, conversation, and connection. To all other participants, we bid you farewell and hope to see you in the upcoming events of the Japan-ASEAN Bridges event series. Please mark your calendars for the upcoming lecture hosted by the Faculty of Science on the 29th of November 2023. We will have another esteemed Nobel laureate, Professor Takaaki Kachita, who will give us a talk on the importance of science for peace building. The lecture will be given at the Pradit Choijit Lecture Center, also known as the Pumpkin Building at the Faculty of Science. So we look forward to seeing you again on the 29th of November. Thank you for joining us and enjoy the rest of your day.